Hello, my lovers, back again. Stats again. October 2021 this time. So let's get going. We want one disadvantage of using quota compared with simple random sampling. Well, it's not random. Nice and simple. Another one we could say for this is it's biased, or it is not. We can't infer from it, so there's no inference. No inference. Any of those would be fine. Next bit then, in a university, 8% of students are members of university dance club. Random sample of 36 is taken from the entire university. X represents the number of those students who are members of the dance club. Using a supermodel for X, find the probability that X is 4. So we want our binomial calculator. We want to get the PDF. So this being equals is PDF, yeah? So let's look at this stuff. Probability, what do we have? 8%. So getting that up. What we're going to have, 0.08 for that one. Oh, without those bits at the front though. 0.08. Number of trials we're doing, 36, isn't it? 36 people. Looks good. And successes we wanted was 4. So then, calculate. What do we get? Top row from that, the equal, 0.16739. Does that look good to me? Yep, looks spot on. Let's circle the answers we've had so far. All of them in it are good. That one looks nice. Greater than or equal to 7. Change this 4 to a 7. What do we get from this one then? So greater than or equal to 7 is that bottom row with all the 2's. 0.2224. There should be a 0 before those 2's though. Does that look good? It does. Yep, looks very good. If your calculator can only do the CDF, so just a note then, the CDF, let's do this in blue, always means that probably is X, well in this case, yeah, X is less than or equal to a number. So just try and make sure that when you do the 1 minus, so I think this one is, yeah, X is bigger than 7, or equal to 7. It's the same as 1 minus, probably of anything else happening. So if we want it to be less than or equal to, you just have to make sure that all the numbers are included between these two ranges. So this one is everything 7 or bigger. So if we want something and lower, be 6, yeah. Can't be 7, because we've already got the 7 over there. Can't be 5, because then where's the 6 going? So it had to be 6. And that'd be the same. Then you like plug that in, you'd end up with like 76, yeah. 7776 should pop out just for that thing. One take away it, we'll give you all our 2's. That's with 9 in front of that, yeah. 9 and then all the 7's. So next bit then, only 40% of the University Dance Club members can dance the tango. Find the probability that a student is a member of the University Dance Club and can dance the tango. So looking at that, what we can say, we want to have the 8% that members of the dance club and the 40% that are part of, well, that can do the tango, yeah. So working that out, what number do we get? 0.4 times 0.08 gives us an answer of 0.032. Is that good? Yes, it is. So what that's saying is there's like 3%, 3.2% of the total university students can do the tango, because we knew 8% of them could dance or in dance club. 40% of those can do the tango. So we've worked out, yeah, together, like think about that way around. This 40% is the probability that you can do the tango if you already can dance. It's not just tango. Do you mean? This is what we're saying. This is just tango basically. So we've kind of reverse formulation to get this thing out. And this bit obviously is being the probability that you can dance. So this bit on this side is probably that you can just do the tango. And you can get like the rearrangement of these sort of bits. So lovely, that looks good. A random sample of 50 students is taken from the university. Find the probability that fewer than 3 of those students are members of the University Dance Club and can dance the tango. So what we want in 50 people, and we're going to basically use the probability that we've just found. So yeah, because it's from the entire university, that is the 3.2%. So what have we got? Some binomial distribution. Let's call it y. Why not? And it's going to have 50 as the number of trials. The percentage is what probability? 0.032 for the 3.2% chance that a random student from the entire university can do the tango. So what do we want to find? We want fewer than 3. Fewer than 3. If you're doing the CDF stuff, this is going to be y, therefore, is less than or equal to 2. Yeah, anything less than 3. Same answers. These are all the same things. We can really go and put this like over here. It means the same thing. Let's do that. There we go. No. Come on. There we go. Lovely. Let's use our calculator then. Change this value. Success now is 0.032. Number of trials has changed to 50. And the number we're interested in, we could do 2 or 3. We'll do 2 just from the question. Just from the CDF, just so they can see it straight away. So less than or equal to 2. We have that number of, that middle one there, 78508. Does that look good? Looks very good. Spot on. Number 1 done. Number 2 on the way. Mark took a random sample of 16 students. Okay, that's our sample size. He's got the length of their names, first and last name. So his results are shown in the scatter diagram on the next page. So X is last, Y is first. This is last, this is first. Initial observations, looks like it's kind of going down here. Not too much, but it's definitely going down. It kind of, let's do something like that to keep a mark of it. Nice, that looks good. Okay, it's going down, then it negative to describe that correlation. Spot on. Mark suggests that parents with long last names tend to give their children shorter first names. Comment on Mark's suggestion, giving a reason for your answer. So yeah, it looks pretty good, doesn't it? Like, you can see that fits. The longer we make the last name, generally the shorter the first name is becoming. How do we phrase that then? Well, in these ones, just look at the mark scheme. What are they actually saying? So the words they've actually used, his suggestion is compatible because it's negative correlation. So compatible because negative correlation. And these are like the underlined words, do you know what I mean, in the mark scheme? So on these like explain ones or comment ones, just see what they want. See what they say, do you know what I mean? Easy peasy. Nice, what have we got then? We have the actual observations. Okay, use your calculator to find this value. So nice, I don't have a calculator like here, set up ready to go for that. But we can just see what the mark scheme says. We are going to get 0.4259 for that one. Lovely. Nice, let's keep going. Test whether or not there is evidence of negative correlation between the number of letters in the last name and in the first name. Okay, so hypothesis test. We're always going to have a null hypothesis, which for correlation is that there's no correlation. Our alternate is that there will be. Do we have a direction? Yes, negative. So it should be less than 0. We have our significance level, 5%, so 0.05. And what we have is that, yeah, it's a one-directional test. So we can kind of visualize it. Let's draw out some distribution. This is going to be our correlation. And we're going to have some shape then that does something like this. Let's try and do it a bit better. Should be perfectly symmetrical. My drawing obviously might not be. But it should be perfectly symmetrical, with 0 being in the middle. And these extreme ends being at 1 on that end. And -1 this end. What we've been trying to find then, the 5% tells us that we want to find some value, we'll call it R0, that represents, like if you took just a random set of different variables, loads of different variables, and you compare the correlation of all of them, 5% of them would just randomly have a correlation more extreme than this one. That's the number we're looking for to compare it to the observation we have. So the observation that they've given us, that we found in part C, yeah. So our observation is that 0.4259. And our job then is to find some value of the correlation, this row 0, such that that's equal to 5%. How do we do that? We use the tables. In the formula book, in the back of the book, there is this one for the PMCC. We need to know the sample size. We were told earlier on that that was 16, wasn't it? Yep, 16 in there. So we'll use the sample size column that we have, go down to 16. We're then told the significance level was 5%, so 0.05. We're going to go to, I'll try and make it so it's like the most left-hand column that we have, yeah. There we go. So the most left-hand column is the one we want. We want the row where the sample size is 16. Let's actually write down maybe an n is 16 as well. Using that then, let's see what number we get. I get 0.4259. 0.4259. Is that good? Yes, that is good. So that is our naught. That is, yeah, our naught, which is good. So we can fill that in. It's obviously negative. This whole thing is symmetrical. So the positive negatives, don't worry too much about, like, if you've got a negative value out of a positive one. If you get the positive one, it's just the negative version of it, yeah? We're just looking at one side compared to the other side. So that's good. What do we want to do then? Take the value that we got given. Hold on. These shouldn't be the same value. What have I done wrong here? Oh, this one. Sorry. I just forgot this in the book, didn't I? I just wrote down the wrong answer. That's not that correct one. The correct one for the answer before should have been negative 0.545. Just a quick note, obviously we should have had a negative value, shouldn't we, from the correlation. So that's the way that we could have caught that one spot, like, oh, we didn't actually get a negative number, but we had a negative correlation. So something about that was wrong. But that's going to be all good now. That's the one from the book. So, yeah, we have the same idea, but this number now is correct. The observation, though, is what's changed, and that's become the 545. Negative of that. 545. So our job then is to see on our little diagram, where is that number? Well, it's over here, isn't it? Negative 545. It's firmly in our blue region. Our blue region is very unlikely to occur randomly, just to happen naturally. So what we've said, the observation is just very unlikely, very random. We don't think that just happens naturally. So we have evidence to change our mind that there's no correlation. What we've seen is so unlikely that we think there must be something going on deeper inside there. Hypothesis tests are like the first step of investigation. Is it worth having a look? In this case, because our observation was less than kind of the textbook observation from the diagram of like what is the 5% observation, so that the kind of natural boundary or the critical value that we're going to call it, the critical value, our observation was more extreme than that. So if you think about the size, not worrying about the positive negative, but the magnitude of our number, the observation we had was bigger than that critical value. Just put that in the numbers we had. So the negative 545. That is bigger than 0.4259. And that's going to lead us to reject H0. One thing to note, we only ever accept or reject H0. We're saying nothing about H1. This is just the direction that we're going to like do our checks in. That's all that's there for, really. But the whole goal is like, is this true or not? Do we think that we want to change our mind about this? We're rejecting H0. So yes, we are changing our mind. You should always write this as like a full sentence at the end, yeah? Always write a full sentence for that. And like make it kind of to do with what's on about here. So I would say, yes, this suggests that there is sufficient evidence to reject the null hypothesis, and therefore suggests that there is a negative correlation between, what were these two things? The length of first name and the length of last name. Lovely. Looks good to me. Let's keep going. So what do we have? Sav is studying the large data set. He's coding the mean daily pressure with this thing. So it's taking off 1010. Data for all 30 days are summarized. State the units of the variable x. Well, it's the pressure in it. So is it hectopascals? Yeah, HPA. That's good. Find the daily mean pressure for these 30 days. So it's the mean. So mean of that, they're calling it y, yeah? No, we're calling it x still. It's still x for a second. So the mean of x is x over n, or the sum of x over n. Why is it still x? Because we're doing the daily mean pressure. Daily mean pressure is x. So we're still using the x values that we should have. Unless I'm being silly and I'm overthinking it. And I'm guessing they're just going to use the model. No, we are just using, yeah, okay, I was being good, I was being smart. So what we're going to do is firstly, we're going to work out the mean for y in the same process. How do you do that? Exactly this. Sum of the y's over how many y's there are. That was 30. So we get a value of about 7, don't we? Was it 7? 214 divided by 30. We get 7.13 recurring. So 7.13. That's good. That's the mean for y. x is just y plus 1, well, 10, 10. So that should tell us that the mean for the x's is that plus the 110. So 1017.13. Yep, mean for the values here was 7. X's, we've just taken every value, added 10, 10 to it. So that would add on the same amount to the mean as well. You can do it this way around. If we have like a function of the mean where we take in our data set, that would be the general like value for the mean. Say we're gonna do the same thing, but take in some linear operation on our data set. So we're taking every value of our data, timesing it by a, adding b to it. What does this do to the normal, like the mean we did have beforehand? Well, it takes that mean, so let's move everything over a bit, and it's going to times it by a and add b to it, which kind of makes sense. If you double the values, it doubles the mean. Add 5 to the values, add 5 to the mean. So this is the thing that's always true. Basically means that the mean is a linear operator. You can do linear things to the values inside it, and it just does a linear thing to the actual value itself. All sounding good, yeah? Hopefully. So let's keep going then. That was part B. Part C is to do the same thing, but for the standard deviation. So if we do a very similar thing up here, standard deviation, if we took in some, again, linear combination of our data, well, moving it side to side doesn't change the spread, no? It stays the same. So the B has no effect. And what A does is doubles all the values. Say it was 2, do you mean doubles all the values? That doubles the spread between them as well. Here, though, we're measuring the square of that spread. So it's going to times everything by a squared. So whatever value we did have for standard deviation, we will square it. Well, we'll square the scale factor of the x. And you can see here, they're 1 to 1, yeah? So this is 1. So that's going to tell us the standard deviation of the x's is the same as the standard deviation of the y's. So if we can work out the standard deviation of x, we have standard deviation of the y's. Beautiful, that sounds good. Let's go and do that. So standard deviation of x is equal to the standard deviation of y, which we know from the formula should be the sum of the squares, yeah, over n. Take away the mean of the y's squared. Let us put these all in. I'm just going to move these bits up a little bit, yeah, just to give me some more space. Off you go. What was the sum of the y squares? 5, 9, 1, 2. On the bottom is the n, how many there are, which is 30. Take away 214, all squared. Whack this in our calculator, see what we get. 5, 9, 1, 2, divided by 30. Say it again. 5, 9, 1, 2, on 30. Take away 214, all squared. This gives me a very negative number, which is not good. What's gone wrong? That's not the mean, is it? 214. The mean we found it was 7. We should never get a negative this. It should always be a positive value because it's a variance. It's a measure of spread. Think of it like a length. It should be positive. So if I change that to the correct value for the mean, what do we get? 7.13. I get 146. That's really big, yeah? It doesn't change that much. Like if the sum of all of them is only 214, how is the spread 146? Like an average spread that much. We've forgotten to square root. This formula we've used is for the variance. So we need to square root all of that stuff. Square root all of that as well. So square out the answer on my calculator. 12.1. Lovely. Jubbly. What's next then? Oh, there's win stuff. Okay, yeah. Some of these large data set things I don't know, so it's just I'm just reading the mark scheme. I know some bits, but it's not always true. So we want to think about which way the wind is going. On here, I can't remember exactly how the map was going. So let's just draw a rough thing of the UK. Heathrow is already down here, isn't it? Let me double check where all those places are. So Herne location. Imagine there's a lot of people have been Googling that this week, isn't there? Herne location, where is it? Is that south? Yeah, it's south coast, isn't it? Okay, it's by like Portsmouth, Bournemouth sort of way. Okay, it's down here. And I think the other place I can't say it's like Luchard, it's something like that. I don't know. I have no idea. I want to say it was France, but it's actually Scotland, isn't it? Location. Yeah, town in Scotland. Okay. So this is LEU, Charles. So that's where they are. What we have are these wind directions for them. We're not sure where they are. But what we have is very high pressure. and it goes clockwise in high pressure. So the wind itself is going to be doing this, yeah, rounded that way. But when we talk about wind, we talk about where it comes from. So northerly wind comes from the north, southerly wind from the south. With that then, let's think where are these coming from, which ones are available to us. So looking at the top blue charts first, that could be like a westerly one, do you mean, or a south? That's probably fine. Here, I'm going to guess north for Heathrow, and then probably something eastwise for Herne. Looking at these then, okay, it's going to be east for Herne, isn't it? I'm going to say it's the west then for Luchards. So let's fill these in. So Herne will be the east. Let's cross that out. The Luchards will have to be the west, won't it? And therefore, let's just leave Heathrow with northeast. And that looks good as well, Jimmy. It's coming in that direction. It's coming from the northeast. Looks good. Yeah, lovely. Looks good to me. Let's keep going. Number 4, what do we have? Probability stuff. So lots of things in there. Blah, 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 blah. Don't really need to know. Find the proportion of students who read exactly 2 of these magazines. So exactly 2 are going to be this section, and this section, which looks good to me. Sorry, exactly 1. That I was correct about exactly 2, but we want exactly 1. So it's that one, and that one. We're in just one circle. We're at no point are we in 2 of the circles. So it's going to be 0.08 plus 0.09 plus 0.36. Adding these together then, what do we get? That's 45. Another 8 makes 53. 0.53. Is that correct? Just double check. Number 4. Yep, all good. Big circle. And let's move on. No students read all 3 of the magazines. Okay, so that middle section, P is 0. So we'll get rid of P, don't need it anymore. Just a 0 now. Okay, find the value of P. 0, lovely. Value of Q. Well, we're told probably of G was a quarter, yeah? That's going to be the entire circle, G. Let's add everything up. We're going to have 0.08 plus the 0.05 plus the 0 and plus the Q. Should be 0.25. 8, 5 gives me a 13. And we have a 25 on the other side, so I've got 12 to go. So Q should be 0.12. Does that look good? Does indeed. Next bit then, we've been told about some conditional probability. That's S given E. So let's write that out as the formula. We know it's going to be the intersection S and E over just E by itself, the second one. And that should be 5 on 12. From here then, what do we want to do? Well, we go and look up at the diagram we had, and let's see which bits they are. So S and E are those bits, yeah? So that's R. And on the bottom is E. So that's the whole thing. So it's R plus 0.14, yeah, for those bits. R plus 0.14. And that equals the 5/12 we just found. That looks good. Let us times this bit to the right. So I'm going to have 5 times those bits. 5R plus 5 times 0.14, 0.7. This 12 will send you over there. 12R on that side. If I then take away, I'll have 7Rs equals 0.7. So R is 0.1, yeah? Does that match up? Does indeed. Anything else we need to find? T. So where's T? Up here. Do we know anything else? Let's fill in the values we do actually have. This is Q, 0.12. R we just found, wasn't it? 0.1? 0.1, yeah. I'll make it 0.10. So what's left over is just T, isn't it? Yeah. I have this, this, and this, this, and this, and this. Yeah, just you at the end. Little lonely guy on the outside. So what have we got? 8 plus 12 is 20. 25, 34, 44, 50, 80. So left over 20, get to 100. 0.2 on the outside. Is that good? Yep, that's good. Anything else we need? Okay, determine whether or not the events S intersection, not E, and G are independent. Okay, so S, what we're doing? S intersection, not E. Let's go figure out where that is. So the way to do this, Well, we have an intersection, so we need to satisfy both conditions. We need to be an S and not be an E. So we can go through and just ask the question of every point. Are you an S? No, no, no. Yes, 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 and no. So that can be the blue side. Do you mean that can be blue ones? We'll do the green for the E or not E. Are you not in E? Well, you're not. You are. You are. You are. You are. You're not. You're not. You're not. With the and, we need 2 ticks. So everywhere they've got a green tick and a blue tick is part of our region. So looking at that, where did we get? I got here and I got here. So altogether, it's the 0.12 plus the 0.36, 0.48 together. All make sense, yeah? Another way is, well, we need 2 ticks, so we have to be an S. So I'll just look at these ones, and I can't be an E. So just cross out the ones in E. What's left over? 0.12, 0.36. So that's good. That is, I'm going to make a little list of things I have. The probability of S intersection not E. 0.48. We want the probability of G. I think we got told that somewhere, didn't we? We did something to figure that out, maybe. Yeah, it's up here. 0.25. We're going to want the intersection of those things. So S intersection not E intersection G. Don't worry about brackets here. Think of this like multiplication. If you're doing them all together, then don't worry, like it's like doing 4 times 5 times 3. It's the same as 3 times 4 times 5, etc., etc. Order here doesn't matter at all. Same for union, but if you have like combinations, then yeah, do brackets there. But there's like, yeah, so one is intersection, one's union. I'll do brackets around those. Here though, doesn't matter too. Well, doesn't matter at all. Right then, let's figure out what section that is. Well, it's going to be smaller than this because we've got that condition and an extra condition. So where we had these ticks earlier, we can imagine doing like an and G. Let's do a different color maybe. So this pink, like an and G there, and we can see, are we going to like satisfy that condition too? We need to ask the question now about these two. We did for Q, but we don't for the 3, 6. So our intersection point is just that Q value, the 0.12. We have everything then. Let's fill in the equation that we would normally know for independence. So the thing that's always true if they're independent. We need to check whether that intersection, like the triple intersection, S intersection not E, intersection G, is equal to the product of those two individual probabilities. The S intersection not E and the G. So filling it in, what do we get? 0.12 on the left. And on the right, we have S and E, which is 0.48. And then, yeah, okay, this is good, 0.25. That's a quarter in it, 25. Quarter of 48 is 12. So that is good. Big tick, let's do a bigger tick. And that tells us they are independent. Lovely jubbly. Same works in reverse. Like if we knew they're independent, we could write this fact down. So it's like they're both true or neither true. Lovely, that's all good. Did we do everything on the page? Yep, we have. Let's keep going. So the height of females from a country are normally distributed with a mean of 166.5, standard deviation 6.1, 1% shorter than k centimeters. Find the value of k. Okay, let's call it height. Distributed normally with a mean 166.5, standard deviation 6.1. So it goes in there, gets squared. We want to find the probability that h is less than k, so being shorter than k, is 0.01. So we need to do the inverse normal. We have the probability. We're going to go and find out what was the input. Where is the inverse normal on here? Is it this one? No. No, it's not. It's this one. So what values do we have? Well, the area, that's probability. 0.01. Mean, what do we have? We have a number of 166.5. Standard deviation, does it 6.1. And we want to be below, don't we? Because we want to lower. H is lower than some value. This is the shortest height. So below, let's do below there. Symmetrical. So like if we get, you could work out how far it's from the mean, just do the other way around. But easier, you might as well just do it this way around. That's going to tell us from the calculator that k is equal to 152.3. Don't need all the decimals. 4 sig figures is plenty, yeah. Let's double check that's the right answer. Yep, they even accept 152. Lovely. Looks good to me. Find the proportion of females from this country with heights between 150 and 175. 150, 175. So, other way around now, not inverse normal, just the normal. What numbers have we got? Same numbers, 166.5. Standard deviation, 6.1. And we want to find between, don't we? Between 150 and 175. Calculate. Oh, I get a big one. 0.9148. Does that make sense? Well, how tall is this? Is it 5 foot? Nah, you're 4'11", aren't you? 4'11" there. And that's going to be then for like 5'10", maybe 5'9", something like that. 91% of people being between, or women between 4'11" and 5'10". That seems pretty straightforward. That seems pretty good, yeah. Lovely. It's always worth checking, like, does it make sense? If it doesn't, double check it. Do you know what I mean? If it does, be like, okay, maybe I'll look later. Right, next bit then. A female from this country is chosen at random from those with heights between this. Okay, so that tells us that whatever we're doing, that we'll find that probability now, but it's been given that thing above. 150 is less than H is less than 175. What we've been asked about, height is more than 160. So how do we know it was given that? Just because, yeah, we're chosen at random from those people. Not from everyone. The one that we had before chooses from everyone in that country. Not just the people of like the middle 91% of height, or like this range of heights. So how do we work this out? It is a given that formula. So we want the intersection. We can think a little bit smart here. You could obviously write down like intersection of this and this thing. But what does it mean? We're going to be bigger than 160 and between 150 and 175. Those two together, let's actually write them down as a number line. We can think about being, yeah, between these two. So this is 150, 175, and we want to be bigger than 160. So think about this point, go in that direction. Can go as far as you like, but just being bigger than 160. So we can split off the entire number line into these three regions where we need to be both, yeah, intersection, 2 ticks again. So here I don't get any ticks, do I? Here I get 1 tick, not 2. Here I get 2 ticks, and here I get 1 tick. So what region is that? We want to be at least 160 and at most 175. Bottom then will just be the given that thing. So actually it's going to be this whole thing, isn't it? Let's just steal this. It'll be that thing. Get rid of you. Put you in its place. Lovely. That we do know though. We can fill in the blanks there. The bottom of that is that 9148 we found. And the top we'll get from the calculator. So by 150, I changed to 160. So now we're between 160 and 175. I get a new number of 0.7749. And let's do my division. So what do we have? Fraction 0.7749 over 0.9148 gives me an answer of 0.8471. And that is what the mark scheme says. So that's a good sign. Let's keep going. Well, heights of females from a different country. So different country, but they're still heights, yeah? So I'm going to go and just relabel. Height 1, height 1, height 1, 1, 1, 1, 1. Is that all of them? Yeah, I think so. So height of country number 1. Now, we're going to have a new height of country number 2, which is distributed still normally with a standard deviation of 7.4. So 7.4 squared in there. Mia believes the mean height of the females is less than 166.5. Takes a random sample of 50. Finds her mean sample is 164. So we don't have the actual value of the mean of country number 2. What we're going to do then, she thinks it's less than this one. We're going to test about that. So let's assume that it is. We'll put the 166.5, sorry, assume it's the same, and then we're going to test whether that's true or not. Looking at that then, one thing to notice, this is the way that we would randomly generate, or like the distribution of heights of one person, one woman in country number 2. We have a sample now of 50 women from this country. So we want to find, of the women in country number 2, their heights, the sample of them when we've got a sample size of 50. So that's distributed normally, the same mean, 166.5, but now the standard deviation will be 7.4 squared. Oh, well, this is the variance, yeah, 7.4 squared over the sample size of 50. So our standard deviation is the square root of that thing. Let's just work out what that means. So doing this, it will be 7.4 over root 50. So just square rooting this value, yeah. And we get a number to decimals of 1.0647, we'll say. So that's good. In your calculator, I think you can just do that, but I can't do that on here, Jimmy, so I have to use the decimals. Right then, what do we want to do? Hypothesis test. And what she's claiming believes that the height of females is less than 165. Okay, so our null hypothesis is that the mean is going to be the same, 166.5. And the alternate then was that they're less than 166.5. Do we have an observation? I think we do, don't we? Yep, 164.6. And we did have a sample size as well. What was that? It was 50. So, same as always, let's draw this to kind of understand what's going on. We've got some distribution of the heights of these people, of these women, from country number 2. We're assuming that if we were to draw them out and kind of do like a box plot and see where those of them are, we would have this middle would be at 166.5. We have a level, significance level, yeah, 5%. We need that as well. 5% significance level, so 0.05. So effectively, we wanted to find some number here such that the area of this bit is 5%. And what number is this? This is going to be called the critical value. So yeah, the crit value. Lovely. And then see basically whether or not the observation that we had, which side of the line that's on. So is our value going to be over like here or over here? Two ways of doing that then. One, either find the correct value and just compare it to the observation we have. Like if this is 160, then we're on this side and we're in the OK region. If this number is, if the critical value we get is 165 on the dot, then we're over here and we're in the no-no zone. So not allowed over there. Or what we can do is go and find out what is the percentage of this, like the probability of this happening. So I think this is like a tracker in it, 5% chance, like as we get the area as we go through. So if we can find out what's the chance of this, let's say it's 3%, then we know we're in this zone and have to go on this side of the line. So what can we do? I think the easiest way is to just use the calculator normally. We're going to have a mean of still 166.5. Standard has dropped now, didn't it, to 1.047. And we want to find us being below the observation that we had. We're always looking at being more extreme than that observation. Sorry, 0.6 there. So that 164.6 that we have. When we calculate that, this is what we see. So the probability that our height for the second women, when we take a sample of size 50, is less than the observation that we had, 164.6. That was 0.0348. That's less than 5%, yeah. So what we're really saying is that there's a random chance. If I took 50 women that did have a mean of 166.5, they did have that mean. I took a big population. All that's the mean of it is 166.5. Take a sample of that population, 50 women, And randomly, 3.48% of the time, their mean height will be either 164.6 or lower. It's continuous variable, so like exactly that height doesn't mean anything here. But so there should be a random chance that there's a 5% chance of that happening, being less than this height. What we saw, there's only a 3.8 or 3.48% chance of it happening. Less likely, so more extreme. We found that we live in this zone because we're more extreme than what was going on. So 164.6 was very unlikely. Random chance of that happening is quite low. 3.48% chance of it happening. We saw 5%. So we observed something that's so unusual that we're going to change our mind. This causes us to reject H0. You should always write this as like a full sentence with kind of some context. Do you mean context of the question? So I'd say here, this supplies sufficient evidence to suggest that the mean height of women in country number 2 is less than 166.5 centimeters. Yeah? Lovely. Last one. Last one. What have we got then? Some distribution. This stuff goes up in order, A to B to C. All the quantities are greater than 0, and they are all integers as well. So find the values of them all. It's a distribution. What do we know? If we add them all up, it equals 1. So log base 32 of A plus log base 30, 32, 36. Not good with the numbers, me. Of B plus log base 36 of C should equal 1. This, we have a sum of logs. A sum of log is a log of a product, A, B, C, equals 1. Lovely, this is good. Log rules then. Let's raise both sides to the power 36. A to B to C. So A times B times C is 36. They're all integers. And they're all different. So let's have a look at different ways that we can split up 36. We could write it with a 1 at the front, yeah? That's the smallest number. Can't have another 1 though, but we could have a 2 and an 18. We could have another 1. We could have a 3 and a 12. A 1, a 4, and a 9. 166 isn't allowed, no, because you can't have 2 6s. Next then, let's look at these. We've got 2. We've got a 3. Yeah, so 2 would give us 18, and then 3 and 6. Anything else going to work? 2 and 4, and that makes an 8. No, it doesn't go. Nothing, I think. So then it's down, yeah, 6 and 3 again. The next one, 3, isn't going to work, because then we're left with just 12. 4, we need another 3, so this isn't going to work. So they're all the possibilities. All probabilities are greater than 0. Actually, what that tells us, log of 1. So yeah, let's take this row. Log base 36 of 1. What is that? So let's have a look, double checking. If I'm not mistaken, I think I'm being really silly. It's just always 0, isn't it? Yeah, it is. We can get rid of 36 and just put anything. So of anything at all. What that tells us is A and B and C cannot be 1. So we look at our list down here. Nope, nope, nope. Yes. And we need the order. We've got 2, 3, 6. A must be the smallest, B's in the middle, C's at the top. So 2, 3, 6. That's probably something you haven't been taught. The only fact you've been taught about that is that they all add up to 1. Stats sometimes, probably sometimes. It's not so much calculation, it's about understanding all the different eventualities and thinking about, okay, what's going to happen? What weird things are going on to rule out some of my possible outcomes? And why are they being ruled out? Will make sense, yeah? Lovely. Next one then. We want to think about 2 variables now, but they each have the same distribution as above. Work out the chance they have the same thing. So one way, yeah, let's visualize this in a nice way. It's the last question. It's if you're still here, you want to do some math, don't you? Is it the last one? It is the last one, yeah. So let's have a little, how do I view this question? We have 2 things to do. We need to do x1 and x2. What things can happen when x1 occurs? Well, we can either get A or B, or C. So this is doing x1. We then need to do x2. And you can imagine there's going to be A, B, C. But when we think about this, making them be the same, this second branch, like the second kind of step in the process, we only need the branch that's going to A. The other branches exist, but do not satisfy the condition we're after. So why bother waste the time investigating them when they're not anything useful to us? Same thing happens for B. Same thing for C. We have all the chances, didn't we? I'll just like log of those numbers. So this one, if you think about this branch, they're going to have log of A here, log 36 of A. Exactly the same thing here, log 36 of A. So at the end, it's going to be log 36 of A squared. I'm actually going to work out, like, are they nicer? Do they have any nicer bits? Do you mean A was 2? Is log 36 of 2 any good? Log 36 of 2. No, it's not. I'm going to leave it as that then. So that's good. We'll have exactly the same idea. A was 2, wasn't it? A was 2. Exactly the same ideas then. We'll have now, but with a 3 for the B. So get rid of U, put a 3. Have U twice. And then we'll have the same idea. C was a 6, wasn't it? 2 times 3 is 6. Another 6 gives me 36. So log is 36 of 6. As we calculate these then, you've done this before, haven't you? Down there, down there, down there. So I'm going to have log base 36 of 2 all squared. I always want to write like that, but I don't think you guys have seen that before, so I'm not gonna do it. And this thing then, we get exactly the same with the 3 and the 36 and the 36 and the 6 at the end. And then we just want to add all those up. So it's the sum of all of those. Yeah, let's write it down, do it proper. Duplicate those. Duplicate this. And this one. Add them up. And it's going to give us some number. It's not a very nice number. So let's have brackets, log base 36. I'm wondering if there's nicer ways. Like the 6 is nicer. Oh, and that middle one should be 3. Sorry, not 36, isn't it? Yeah, that should be 3. That should be 3. Let's double check. 2. Close, squared, plus log base 36. Oh, let's do that again. Open brackets. We got log base 36 of 2. Close that, square it. Add on. Open a bracket. Put a log in there. Base of 36. Put a 3 next to it. Close the brackets. Put a squared. Open the brackets. Put a log. Put 36 in the base. Put now a 6 inside it. Close the brackets. Square everything. Don't square everything like that. Just square the log part of it. Press equals. And I get a number of 0.3814. Does that match up? This is question number 6. 3814. That's good, doesn't it? Happy days. Yeah, happy days. I'll have more for you soon enough.